All right, so for number 6 here, we have the mass given to us, okay, 0.4 kilograms, and we're told the frequency is 1 hertz, which means the period is also 1, but it's 1 second, right, because 1 over 1 is 1. All right, so we got that. And what we're looking for here is the frequency of vibration if the 0.4 kilogram mass is replaced by a 0.8 kilogram mass. So what we don't know right now is K. Since it's the same spring in the second instance, can I find K with the first mass? Yeah, and that's what I've got to do. Okay, so I'm going to say that T equals 2 pi times the square root of m over K, and I'm going to solve for K. So remember that first thing I have to do is square everything. Okay, and then I'm just going to switch T squared and K, so that I'm solving for the spring constant of the spring. All right, so I'm just going to have really 4 pi squared times m. That'll give me K because T is 1. All right, so we're going to have 4 times pi squared times 0.4 kilograms. Okay, so our spring constant is 15.79 newtons per meter. Okay, everybody with me so far? Yeah. All right, so now I can use that as K in the second situation when my mass changes to 0.8 kilograms. So I'm looking for the frequency. So this formula doesn't solve for that, does it? So I'm going to have to solve for period and then do what? Yeah, then solve for frequency by going 1 over the period. So I'm going to use this formula here, okay? But now that I have K, I'm going to use 0.8 kilograms for my mass. Okay, so we'll have 2 times pi times the square root of 0.8 divided by our answer from the last one, which is our spring constant. Okay, so we're looking at 1.4 seconds, and I've got to go 1 divided by that in order to get the frequency. Whoops, yeah. So 0.71 hertz. Okay, so multi-step question there. All right. Okay, Thomas, you have one? Number 3, okay. Okay, so number 3, the trick is this. I give you the weight instead of the mass. All right, so right away I've got to calculate the mass by going 8.8 divided by 9.81, okay, so that I have the correct mass to use. All right, so my mass is 0.897 kilograms. Okay, and I'm looking for the spring constant, so T squared equals 4 pi squared times m over K, and I'm just switching K and T here, so K will equal 4 pi squared times 0.897 divided by, 1.1 squared, okay? So when we do that, we should get our 29 newtons per meter, but the key there is to convert the weight to mass. Any other ones? Envelope. 8? Okay, so we got simple harmonic motion. Oh, maximum displacement. I have not taught you that yet because that's what I'm teaching you today. So it's no wonder you had trouble with that one. I haven't gone over that yet. Okay. Any others? All right, then let's have a look at this Hooke's law and simple harmonic motion stuff here that we're going to go over today. All right, so that's lesson 2 in your notes package. Okay, so first thing we're going to talk about in this one is Hooke's law. This is the same Hooke who invented the microscope and viewed cells for the first time ever, because he was a physics guy and was just toying around with lenses. He didn't care whether things were made of cells or not. He's a physics guy. But he said, hey, look at this cool thing I invented. Physics rocks. Here, biology. You suck. Okay. No, he didn't really. But he invented the microscope. Okay, but it was a physics experiment. Most of his research actually was around energy and springs and things like that. Right. So that's what we're going to look at here today. Is what he found out about the energy stored in a spring. Well, not so much the energy, but the force that is in a spring as a result of the changes in shape that go along with it. Okay, so we need to understand the relationship between restoring force. We've talked about that. That's necessary for all simple harmonic motion to occur. Okay, spring constant and displacement. Weirdly enough here, we're using X to represent displacement in this unit. And that is because it is not final position minus initial position in this unit. Displacement is always measured from the equilibrium position in this unit. So we don't use D with the arrow over top. We use X instead. Okay, so that'll be how Hooke's law works. Okay, we're going to understand that energy is still conserved. So we're going to talk a little bit about EI equals EF, conservation of mechanical energy. It is identical to roller coasters in principle. Okay, all that is different is the type of potential energy we'll be looking at. We'll be looking at elastic potential energy instead of gravitational, right? And we're going to tie that into Hooke's law as well as your work lab from Science 10, the one where you stretch the rubber band with the spring scale. Okay, that whole thing fits very nicely into this. David.
Wouldn't displacement always be zero then? Wouldn't it always go back to the equilibrium?
No, we're talking about 1 point. So if I push it this way, its displacement is this many centimeters, this many meters. Yeah. All right, and then obviously the last thing here, understand that EP in some simple harmonic motion is going to be elastic potential rather than gravitational. If we're talking about a pendulum is exactly like a roller coaster. It uses gravitational potential energy, right? But a mass on a spring obviously uses elastic potential energy instead. Okay, so Hooke's law looks like this. The restoring force, or the force in a spring, is calculated by taking the spring constant and multiplying it by the displacement. Right? We already knew from last week that in order for simple harmonic motion to occur, that the restoring force needed to vary linearly with displacement. That was Hooke who discovered that. Okay? He found that the further he displaced a spring from its natural shape, the harder it pushed back in a linear fashion. Right? That's where he came up with this law. Now, why is there a negative in that formula? Well, but it's there even if I stretch it. Right. Okay. The force in a spring is always going to be opposite the direction you push or pull it. Okay? If I push a spring in, the spring pushes out. If I pull the spring out, the spring pulls back in, right? So the force, the restoring force, is always opposite the displacement. That's why the negative has to be there. It makes sure that we get the right vector on our force, okay? Because force is obviously a vector quantity, right? So that's why we have the negative in there. This is all Hooke did to come up with this law. He hung a spring from the ceiling, and he hung masses from it and measured how far it stretched, okay? He found that when he put twice as much mass on it, then there was obviously twice as much force. This spring would be twice as long. Okay, it was a perfectly linear relationship. Okay, and that's where he came up with Hooke's law from. Okay, so force 1, and then obviously twice the force with twice the mass. Okay, we've got twice the displacement. All right, so Hooke's law describes the relationship found in springs. Okay, that relationship is that the force required to stretch or compress a spring increases linearly the further it is stretched or compressed. Okay, so that's Hooke's law in words. Hooke's law algebraically. Restoring force is negative K times X. Okay, super easy formula to use. Okay, if I have a horizontal spring, okay, so gravity is not a factor, right, and I push it inwards, okay, the spring pushes back. If it's on a frictionless surface and it's horizontal, the force in the spring is also the net force. It would be the only force in the system. Okay? Once I let it go, it's going to oscillate back and forth, and the only force in the system will be the force the spring exerts. It will cause everything to happen. All right? If this is the net force, then I can say that negative K times X equals M times A. That's why we couldn't do a couple of the questions that were on the sheet before, is because they were asking for acceleration. This is where we get it from, from Hooke's law. If the force in the spring is the only force, it is the net force, and then as a result, I can calculate the acceleration that the object would experience at any point in its oscillation. It's even when it's vertical, but we deal with it mostly when it's horizontal, because you bring in gravity, it'll stretch a little more in the negative direction than it will in the positive direction, right? Just because gravity pulls it harder. Everyone okay with that? Now, if we're talking about just like what Hooke did, which was lower the mass from, or hang the mass from the ceiling, then it's not oscillating. He would just put the mass on there and lower it until it stopped. Okay, then we're saying that negative K times X would equal what force? Fg. Okay, this is how he calculated the spring constant in the spring he was using. He measured how far it displaced, and he knew the mass he hung from it, and he knew acceleration due to gravity. He was able to calculate the stiffness in the spring, okay, as a result. So, okay, those are really the only two situations we're going to run into using Hooke's law. Okay, is that either Hooke's law, negative K times X is the net force, or it's equal to gravity. Okay, the thing about Hooke's law is it will only talk about one point. Okay, even if the object is oscillating back and forth, Hooke's law can only deal with one spot in that oscillation at a time. Okay, because the displacement has to be for this spot or it has to be for that spot. I can't compare two spots. Okay, everybody all right with that? Okay. All right, so it's kind of the same thing here. Okay, negative sign ensures that the force is always directed opposite the displacement. So if I displace it in a positive direction, the force is negative. If I displace it in a negative direction, the force is positive, and so on. Okay. Now, elastic potential energy in a spring is related to Hooke's law, because the further I stretch or compress a spring, the more force I exert, the farther it goes. Okay, that means this, work is equal to force times distance. Okay, the force I exert on a spring multiplied by how far I displace it will give me the work I have done. The work I have done becomes what kind of energy? Potential, elastic potential energy in the spring, right before I release it. Obviously, after I release it, it can become kinetic. Okay, so the more I push on it, the more work I do. So that's related to what you did in Science 10 when you did your work lab with the spring scales and the rubber band. You had a force versus distance graph. Okay, and what you had done was you had distance was the manipulated variable, and you were recording the forces that were required to pull it whatever, however many centimeters at a time. Okay, what you got was this relationship. Okay, showed a linear increase, just like Hooke's law would predict it would. Okay, then you were asked to calculate the area underneath this graph in that lab. Okay, how did you do that? How do you calculate the area of a triangle? Right, half the base times height. All right, so when I do that, okay, I'm going to have 1/2 base times height. All right, what's the height? Well, actually, it's the force, right? Sorry, did I have this the wrong way? No, I don't. Okay, and then the base is the distance. Okay, everyone all right with that? Okay, so when we did that, we were essentially going force times distance. We were calculating the work that we had done. Okay, which meant we were also calculating the elastic potential energy that we had put in the rubber band. Okay, everybody follow me on that one? All right. So what we're doing here when we do this, okay, is we're essentially taking the force, which is Hooke's law, the force in the spring, right? So it would be K times X, and we're multiplying it by X again, right? The distance is this, okay? So, and we said that it was going to be 1/2 the base times the height. Well, 1/2 K times X is 1/2 kx squared. Okay, it's force times distance for a spring. Right? Everybody all right with that? Okay. Everyone follow where we get this formula from? Okay, we're taking Hooke's law, the force in a spring, multiplying it by the distance. Okay, it's a triangle, so it's 1/2 K times X, okay, which gives us 1/2 kx squared. All right. Yeah. So when a mass oscillates back and forth, it's doing exactly what a roller coaster does. It's converting potential energy into kinetic and kinetic into potential, back and forth, same as a roller coaster does when it goes up and down, up and down. The amount of mechanical energy is always conserved. All that changes is how much of it is potential and how much of it is kinetic. Okay, where does it have the most potential energy? Okay, when it's compressed or when it's stretched its maximum amount. Okay, that position, we had a name for that. The maximum amount that a spring can move from equilibrium in either direction was called, started with A. Amplitude, right? Okay, at its maximum amplitude, it would have only potential energy. Where does it have the most kinetic? What do we call the middle? Equilibrium, right? At equilibrium, the spring isn't stretched or compressed. It's not pushing or pulling there, which means there's no potential energy. But that's also where it's been pushed to, right? The spring has been pushing or pulling from amplitude all the way back to equilibrium, okay? That's where it's going to be moving the fastest and where all of its energy will be kinetic. Anywhere in the middle, it's going to be a mix of both. Okay, we'll have some kinetic and some potential, okay, in the in-between places. So when we're looking at this, okay, the equilibrium position is right here. Okay, because the force is equal to 0 there, and we're at our maximum speed. So at equilibrium, we're at our maximum speed. Okay, here at this point, we're not at equilibrium, so we have some kinetic energy, but we also have some potential energy. Out here, our speed is 0, so we have only potential at that point. And similarly, when we compress the spring, okay, we'd eventually get to a point where our speed was 0, okay, and our displacement was its maximum, where we'd only have potential again. So it's going to oscillate back and forth, just like a roller coaster going up and down, okay. So we see that this formula sets up very much like what we did with roller coasters, except instead of having m times g times h, we have 1/2 kx squared instead. Okay, so all we're doing is substituting in a different kind of potential energy instead of gravitational. Okay, the rest of it is exactly the same. You manipulate to find either x or v, okay, and you'd go from there. All right, now, unlike gravitational potential energy, we can't cancel the masses off because mass is not in every term. Right, so that's a little bit different as well. You'd have to keep mass in there. Mass actually matters here. Okay, all right, questions there? So we'll stop right there and we'll head over. So as we were saying here, these conservation of energy problems are going to work very much like roller coaster problems from before. Okay, we're just substituting in elastic potential energy for gravitational. Okay, and what may end up happening occasionally as well as a question like this could lead to a Hooke's law kind of question that says, at this point, what would the acceleration of the object be? Okay, and then you would have to calculate it using that negative kx equals m times a type of calculation. All right, so that's kind of where we're moving to. So we're going to do a few examples here because there's really not, I don't have to teach you law of conservation of energy again. You guys already know it. You've been, doing it since Science 10 and we did in Unit 2. Okay, we're just going to look at some different examples here. All right. So this is a lot like the lab that you guys did in grade 10, okay, where you had an elastic object. This time it's a spring instead of a rubber band, okay, and it was pulled to various distances, okay, and then they asked to plot a graph. We're not going to do that, but obviously we would see a linear fit, and the area underneath we already talked about would be the potential energy. Okay, so if we have a graph like this is exactly what we were looking at, displacement and force, okay. Now, here's the other thing. What's the slope of this line going to be equivalent to? Nope. I've got force divided by distance. That gives me newtons per, right? Slope is k, doesn't change, right? The slope of that line doesn't change. It's the same spring, and you just keep pulling it further and further. The one consistent thing for every time you pull it is the constant of the spring. Hence, constant. It doesn't change. Okay. All right. So let's try this one here. We have a spring that has a spring constant of 30 newtons per meter. It's pulled. Okay, so we know what K is. So you might want to write this one down as your first example. Okay, 30 newtons per meter. It's pulled a distance of 1.5 meters from equilibrium. Okay. What's the restoring force? All right. So instead of writing D, we would write X because it was measured from equilibrium. All right, did they tell me which way it was pulled? No, I'm just going to assume then that that's a positive number, right? Which means my force is going to end up negative, right? Because I just have to plug it in F equals negative K times X. Okay, plug in my numbers, 30 times 1.5, and I should have a force of 45 newtons. Negative 45 newtons.
So when it's like if it doesn't give you the specific directions, do you always assume that it's positive?
Then you assume it's positive. Yeah, if they don't tell you, like this is a poorly worded question, it really should say right or left or something. Okay. Everybody okay with how that one worked? Okay. Hooke's law is not terribly difficult, right? Pretty easy formula. Okay, try 1 and 2 there. They're pretty straightforward. Okay, number 1 is basically the same thing we just did. And number 2, okay, we're given a force and we're given the distance. So you're looking for the spring constant in that one. Okay, so for question number 2, they say the spring requires a force of 100 newtons to compress at a displacement of 4 centimeters. We're looking for the spring constant. Spring constant can't be a negative number. Okay, spring constant is something inherent to the spring. It works equally in either direction, whether it's stretched or compressed. Okay, so what I have to recognize here is that these two numbers have to be what? Opposite. One of them needs to be negative. Okay, they can't both be positive. My displacement and my force have to be in opposite directions. They just have to be. Okay, according to the formula, okay, where the restoring force in a spring is negative K times X, okay, this force has to be in the opposite direction of X. Everyone with me on that? All right, so either the 4 centimeters is negative or the 100 newtons is negative. Right, I'm going to make the 100 newtons negative, right, when I do this problem. Right, so I'm manipulating to try and solve for K. So what I'm going to do is bring the negative and the X over to this side. Okay, so what I'll have is negative 100 newtons divided by negative 0.04 meters, because it was in centimeters. Okay, and when I do that, then I'm going to get my 2,500 newtons per meter, and it comes out with no sign, okay, which is as it should. Okay, everybody all right with that? In the event that you mess up or that a question isn't very clear and you end up getting a negative number for K, do you write it as negative? No, K can't be negative. Okay? K works equally in either direction. Okay, and that'll happen sometimes. You'll just forget, or a question will just be poorly worded or something like that, and you might end up with a negative K. Just know K can't be negative, and you don't write it that way. Okay. All right. Okay, so this is a good one here because we have a vertical spring this time. Okay, something like what Hooke was using. We have 510 grams attached to the spring. That needs to be in kilograms, so we're looking at 0.510 kilograms. Okay, it's attached to the spring. The spring stretches a distance of 0.5 meter. All right, we're looking for the spring constant. All right, so here's what we have to keep in mind then. What force is stretching the spring here? Gravity. Okay, so that means since it doesn't say that it's oscillating, the net force must be, okay, or the force that it's working against is gravity, which means actually the net force in this case is 0. This plus that would equal 0 because the mass is not oscillating. Okay, the spring is pulling up with the same amount of force as gravity is pulling down. That's why it's not accelerating. Okay, all right, so I'm trying to find the spring constant here. What do I do with the X? Right, take it over to the other side. I'm going to bring the negative along with it. This is one of the questions where you're actually going to end up, just because of the way it's set up poorly, okay, that K might come out negative. If that's the case, no big deal. Okay, we just know K can't be negative. I would probably just ignore it. Yeah, because K can't be negative. Yeah, in a question like this, I would understand why it would happen. Okay. All right, so I'm going to bring K over to the, or sorry, X over to this side. Okay, divide both sides by negative X. That's going to leave me with K. Right, so here's what I'm going to have. 0.510 times negative 9.81. I'm assigning down as negative here. The spring is pulling up, right, which would be positive. Here's the problem when I do that. I have a negative times a negative on the bottom, which will give me, right, and then I'll have a negative on the top and a positive on the bottom. I end up with a negative K no matter what I do here. Okay, it's just one of those weird situations where it comes up. Okay. Okay, so when we do this, okay, yeah, we end up with a negative number. Okay, that's going to be a little bit off, but we just recognize that that isn't possible. All right, so our spring constant is 10 newtons per meter. Came out negative simply because I had two negatives on the bottom. Sorry, I forgot to draw the other one there. Okay, but we let it go just because we know that can't happen. Okay. We know that the spring is pulling upwards. Everyone okay with that? Okay. And we're not going to do the multiple springs because we don't have to. And that's a vertical one, so we don't have to do that either. Okay, so let's have a look at number one because we haven't done one like that. We might run out of time, but we'll give it a try here. Okay, so we have a 0.724 kilogram mass oscillating on a horizontal frictionless surface attached to a spring whose spring constant we know. Okay, they're asking us what the acceleration is, okay, or sorry, what the displacement is when the acceleration is this. So if it's a horizontal spring, the only force acting is the spring. So that makes the spring the F net. So this is one of those negative k times x equals m times a type of problems, right? In this case, we're looking for x. We know k, we know m, and we know a, right? So we can solve for what x would be. We'll have m times a over negative k, okay? And we're looking for that. So we would just multiply, and we'd figure it out from there. Talk about that one, start it tomorrow. Actually, no, we won't, because tomorrow you have a test. So we'll start talking about that Thursday after I go over the test, okay, with you. So on question number one, we know our mass is 0.724 kilograms, okay, and it's oscillating, going back and forth on a frictionless surface attached to a spring whose spring constant is 8.21 newtons per meter, okay? What is the mass's displacement when the acceleration is 4.11 meters per second squared left? Okay, so it's on a horizontal frictionless surface. What is the only force causing the oscillation? Force of the spring. Thus, the force of the spring is the net force. All right, so this is where we have this situation. Okay, we can calculate this because we know the acceleration at whatever point we're at. We're trying to find that point. We're trying to find what x is when the acceleration is 4.11. So I'm going to solve for x by dividing this side over here. Okay, so I'm going to have that x equals m times a over negative k. Everybody all right with that? Okay, so I am going to say that left is negative. Okay, I'm just going to establish that as negative. Okay, so I'm going to plug in my numbers here. It's going to be 0.724 times negative 4.11, because I said left would be negative, and then I'm going to divide by negative k, which was 8.21. Right. When I do that, I should get 0.362 meters, and it'll be positive, so it'll be to the right, because I said left would be negative. All right, so when I punch all that in, 0.724 okay, times negative 4.11 divided by negative 8.21, okay, 0.36, right? So that they got 0.362 okay, meters to the right. Okay, everybody all right with that? Yeah. Okay. Now, number two is a law of conservation of energy question. Okay, so I want you guys to try that one, see how you do on that one, then we'll walk through it together. But it is a law of conservation of energy question. So it's an EI equals EF kind of situation. All right, I'm going to give you a few minutes on number two, okay, and then we'll walk through it together. Yes, you can. All right, so for question number two, okay, we're dealing with two different places. That's how we can tell the difference between a law of conservation of energy question and a Hooke's law question. This object is oscillating back and forth. It talks about the maximum amplitude and then wants to know the maximum speed. Those occur at two different places in the oscillation, right? So what we're being asked to compare is the energy at maximum amplitude with the energy at, where does its maximum speed occur? At the center, which we call equilibrium. Okay, so we set this up like law of conservation of energy. We'll say the initial potential plus the initial kinetic equals the final potential plus the final kinetic. However, we'll be able to eliminate a couple of these because a few of them are 0. At the maximum amplitude, there is no speed, so thus there's no kinetic energy. At the maximum speed, there is no potential energy. So what we're left with is the initial potential equals the final kinetic. In other words, 1/2 kx squared equals 1/2 mvf squared. Sorry, that should have an I beside it there. Okay. We have all of this information. Here's x initial, okay? Here's our spring constant, here's our mass. All we have to do is solve for VF. All right, so if I want to get VF by itself, what do I have to do with the half and the m? Divide. All right, what's going to happen to the halves? They're going to cancel. All right, and what do I have to do next? Square root it. All right, so now I'm solving for VF. So VF will equal the square root of 4 times 1.12 squared, that's the most common thing forgotten, is to square x, okay, divided by 0.05 kilograms. Okay, so when we do that, okay, so 4 times 1.12 squared, okay, divided by 0.05. All right, so it's moving at 10 meters per second at equilibrium. All right, everybody okay with that? All right, does it become any harder if I'm not dealing with those two positions, but I'm dealing with like two positions where it has both kinds of energy, like kinetic and potential? It's no different than a roller coaster halfway down a hill. All right, you're just gonna have to manipulate a few more things around. Okay. We'll skip number 3 for now. Okay, this one's a little bit more challenging because you got to combine two concepts on this one, right? It's looking for the period of oscillation, but you actually have to do some other calculations in order to get the information you need to get the period, right? So it says it's oscillating with this amplitude, 0.1225 meters, right? So that means I just write A, I know it's the maximum X, okay? 0.1225 meters, okay? Has a maximum speed of 5.13 meters per second, okay? And we know that K is 5.03 newtons per meter. If I want to find the period, okay, what don't I have? Mass. Okay, can I use this information to get the mass? Okay, do it. So we don't have the mass of the oscillating object here, and we need that if we're going to calculate the period of its oscillation. So what we do have is enough information to compare this point, the maximum amplitude, with this point, equilibrium. What's the same at those 2 points is the mechanical energy of the mass. Okay? At the maximum amplitude, which we'll say is the initial point, all of the energy is potential. So I often write, when it's at the maximum amplitude, I often write it like this. Instead of saying X, I actually write A. So I know this is the biggest X. Okay, it's different than all the other X's. This is as big as it can be. Okay, and that's going to equal 1/2 mv max, so that I remember this is at equilibrium, squared. Okay, there's no potential energy at that point. There's no kinetic energy at this point. These two things are equal, and I know everything except for the mass. So I'm just going to isolate the mass by dividing both sides by half of V max squared. The halves will cancel, and I'll be left with just m over here. So m will be 5.03 times 0.1225 squared divided by 5.13 squared. So that'll get me my mass. Okay, so my mass is very, very tiny. All right, it's like 2.8 grams or 2.9 grams. Okay, it's very, very small, and that's fine. It's a small mass. Okay, so I've got that for right now. That's my mass. Now I can plug it into this formula here and solve for what the period would be. Now it's not oscillating very far, and it's quite small, so chances are the period's going to be very small, okay? All right, so all I have to do is just plug directly in. I've got all the other numbers here, so that's what I'll do. We'll have 2 times pi times the square root of our answer, which was the mass, divided by 5.03. Okay, so the period of that oscillation is 0.15 seconds. Okay, so it's pretty small. Okay, questions on how that one worked? Okay, it's not often that you would get one that would combine those two concepts, but it's not outside the realm of possibility either. Okay, these kind of questions calculating the period are pretty easy, so throwing in a little bit of conservation of energy is not to be unexpected. Okay, so I want you guys, we'll just try question number 1 and then we'll leave it at that for today. Okay, so I'll just make it big enough that you can see it. Okay, so try question number 1 there. Hopefully we'll get a chance to walk through that before class ends. All right, let's look at A. All right, so we want to find the acceleration of the mass when its displacement is 0.3 meters. I don't need the 0.8 for this part, okay? It's a horizontal spring. So the force, the restoring force is the net force. I'm just looking for acceleration, so I divide both sides by m. What I'll have there is negative 40 times 0.3 divided by the mass, which was 2.5 kilograms, and that should give me negative 4.8 meters per second squared. Okay, that's our acceleration at that point. All right, to calculate the maximum speed, now I want to use this. Remember that that's the amplitude. At the amplitude, what kind of energy do we have? At the maximum amplitude, we only have potential, right? And then maximum speed occurs at equilibrium. So really what we're saying here is, yeah, EI equals EF, but we're saying it's 1/2 Ka squared, where the maximum potential energy occurs, equals 1/2 MV max squared, right? We're solving for that maximum speed again, right? So we'll have the square root of Ka squared over m equals the maximum speed, right? So that'll be 40 times 0.8 squared, okay, divided by, what was our mass? 2.5 kilograms. Whoop. And then square rooted. Okay, so we're looking at a maximum speed there of 3.2 meters per second at equilibrium. All right, then to calculate period, t equals 2 pi times the square root of m over k, right? And we have those. We've got k, we've got mass, so we can calculate the period pretty easily there. Okay. All right, tomorrow, unit exam. Make sure you come ready to class. You need, some pencils, a calculator. Okay. Yeah, we'll do the same thing we usually do. Guys, come in, let's say about quarter after. Okay, quarter after, and you can start then. I don't remember. This test is super short. If you start at a quarter after, you could be done by 1 o'clock. Yeah. You don't really I think need to come in early, but